Assalamualaikum and salam sejahtera. So in this video, we're going to discuss about inverse Laplace transform. So after we do all the analysis and design in S domain, in Laplace domain, so we want to know what is the actual form of response or the effect of the design in time domain, because we can only visualize in time domain because that's our domain. Laplace is just a design domain. So what we need to do is we have to transform from Laplace back to time domain. Okay, so this is the operation how we're going to transform. Okay, we use this equation how to inverse back from Laplace into time domain. And the symbol for inverse Laplace is L upon of minus 1, that means inverse. Before that, L to indicate Laplace transform, L upon of minus 1 indicate the inverse Laplace transform. So this is the function that we're going to use to transform back from S domain into time domain. But don't worry about this because we're not going to do the integration, but instead we're going to use Laplace table to do the inversion. Okay, so don't worry about this complex equation. Okay, but for now, let's see how we do it step by step. Okay, let's say you have general function or transfer function like this. Okay, and the top you have root of the numerator. As we know, before this we already discussed the roots of numerator, we call it zeros. Okay, and the roots of denominator, we call it poles of the system of the transfer function. Okay, there are two ways, there are two approaches to do inverse Laplace. First is partial fraction expansion, and the other one is method of residues. Okay, so we're going to discuss about partial fraction expansion in this video. And of course, method of residue is the method that has been used numerically by MATLAB. So I will demo this using MATLAB, and we're going to discuss about this immediately. Okay, so what is the partial fraction expansion? Okay, let's say we have the function like this or transfer function like this. So we're going to expand this or break this into a fraction like this. The roots of this, okay, the first one is s plus 1, s plus 3, for the second one, and the third one s plus 4. So we're going to break this into four roots of the denominator. Okay, so and at the top we're going to put a, b, and c. Later on we're going to calculate this value of a, b, c. Okay, so how to calculate a, b, c? For non-repeated linear factor is quite easy because all the roots here are non-repeated and also not complex conjugate. Okay, so this is what we call non-repeated linear factors. Okay, so first for the first one, how to calculate the a? So you take this s plus 1. Okay, you take out this, so you cover this. Okay, just take the rest and substitute s equal to minus 1. So s plus 1 here, you put equal to 0. So as a result, you have s equal to minus 1. So you take this part of the function, which is independent of from these roots. So you get this. And set the s equal to minus 1. Okay, you substitute the value here. You're supposed to get the value of a. In this case, you substitute s equal to minus 1. You're supposed to get here a equal to 1 over 3. So you repeat for b. For b, you take out this part, s plus 3 from the function. Okay, so just left with that one. So you get the function here. And now you substitute s equal to minus 3. So substitute s equal to minus 3, you're supposed to get minus 5. Okay, and similarly for c, you take out this. Okay, you get that function, substitute s equal to minus 4, you're supposed to get here 17 divided by 3. Okay, so then this equation you can write here equal to this function. Okay, so after you get this partial expression, then you go to Laplace table, look at for this function in Laplace table. Okay, we look at this function. For example, the first one, s1 divided by s plus 1. Okay, it looks like this one. 1 divided s plus a. In this case, that means a equal to 1. And we know that this in time domain will be e of power of minus at. A in this case equal to 1. So we have the time domain e of power of minus t. And this multiplier is just a linear theorem. So you just bring this to time domain. Okay, we learned that before in the first video. There's a time scaling theorem. So the scale just linear theorem. So we just bring this multiplier to the time domain. Okay, similarly for this, if you see that 1 divided by s plus 3, so now a equal to 3. Okay, so over here you have e of power of minus 3t. So a here equal to 3, and then bring the 5. Similarly for this, you get a equal to 3, so e of power minus a power 4, so you get here this term, and then carry power 17 divided by 3. So this is the inverse Laplace of that function just now. Okay, so this is the time domain equivalent. Then we can imagine from here. So we see that we have 3 decay function. So when we combine this together, we know that the graph is something downward with exponentially converge. Okay, so let's try to say this when you have repeated roots. So in this case, the function will have one repeated roots here, which is s plus 1 squared. So the root is repeated at minus 1. So what we need to do when we do partial expansion, we have to do something like this. So s plus 2 as usual, doesn't matter as before, as the previous example, but this one you have to expand into 2 terms. Okay, s plus 1 and s plus 1 squared. So it's become 3 term there. Okay, so to solve for this c is the same as before, and to solve for this a also the same as before. Okay, for example, for c, you just take out this, so you have with this, you left with this. Okay, and then set s equal to minus 2, so you should get 4. Okay, sorry, for b, it is same as before. So b, so you take out this part, just left with that part. Okay, and you set s equal to minus 1. Okay, and then you get 1 for b. But for this one, you cannot do like that. Okay, so for a, so what you need to do for a is you have to differentiate first. So you differentiate, you multiply the function, this function multiply with these repeated roots. Okay, multiply this f with the repeated roots. That means you take out this. Okay, you just left with that one. Okay, and you equate to that side. Okay, that means you multiply both sides. So this one multiplied by s plus 1 squared, you become like this. This one you just have b. This one you have s plus s squared at the top. So after you multiply that, and then you differentiate the term. Okay, you differentiate this. If you still remember, we have to use this rule of the differentiation. So you're supposed to get something like this when you differentiate this function. Okay, you're supposed to get something like this on this side, and on this side you're supposed to get something like this. So you differentiate this, so s disappear, you just have a. You differentiate b because b is constant, so it becomes 0. So you differentiate this. Okay, again using this rule, you're supposed to get this. Okay, so after you get this differentiation, so you set s equal to minus 1. Why minus 1? Because we're still talking about the root of s equal to 1 here. Okay, the repeated roots. Okay, set s equal to 1 here, s equal to 1 here, and then you are ready to calculate for a. Of course, c, you substitute the c that you have calculated before, so you left only unknown of a. So you rearrange that or substitute straight away, then you should get the value of a equal to minus 3. Okay, and then this expression or partial expression become like this. Okay, with the value of a, b, and c. Okay, so it become like this. So now we know that we can see this from the Laplace table. Okay, so for the first case, it's this one, a equal to 1, so you get e to the power of minus 1t, multiplier is minus 3. Okay, for the second one, so it's the same as this one. Okay, s plus a squared, and a equal to 1, so in time domain is t e to the power of minus at, where a equal to 1. So you have t e to the power of minus t. The multiplier is just 1. Okay, for this one, it's the same as this one. Okay, so a equal to 2. Okay, so you have e to the power minus 2t, and the multiplier will be 4. Okay, so this is the time domain equivalent for the f function just now. Okay, if you have a complex conjugate roots like this, or we also call it quadratic factors, so you have something like this, then you have to express the partial fraction in terms of something like this. The or normal linear roots like this for this one. Okay, just as usual, a divided s plus 1, s plus 2. But this part, the quadratic factors or complex roots, the one that you cannot factorize unless you will end up with complex conjugate roots. So you have to express in terms of something like this, bs plus c divided by that. Okay, and you can prove mathematically that this one will always end up with the cos and sine in this form, something exponential with the scaling multiplied by cos, and beta scaling multiplied by exponential um, multiplied by sine omega t, something like this. So we're looking for something like this in Laplace transform. Okay, so to calculate for a is as usual, you take out this part, so the rest you substitute s equal to minus 2. Okay, set s equal to minus 2, you're supposed to get a equal to 1. Okay, but for b and c, this is what you need to do. Okay, you take the numerator part of the equation. So this numerator part you take from this side and also this side. But before you take the numerator, you must make sure that denominator will be the same. That means you have to have the same denominator from left to right side. So that means this s plus 2 must multiply with this, and this must multiply with the a. Okay, and then you equate. Okay, so you get this expression. But of course, in this case, you already substitute the a equal to 1 because we already know the a. So after you equate this, you collect the term. Okay, the power of s squared, power of s, and independent of s. So after you do this, then you equate the multiplier of the same power. For example, in this case, you have b s squared equal to s squared. So like this. Then you know that b equal to 1. Okay. And then similarly for this, the term that independent of s, here you have 2c, here you have 4. So you have 2c equal to 4, then c equal to 2. Okay. So basically, the last equation is just to double check, to make sure that you get the correct value, then your calculation is correct. Okay, so now the game is how to express in terms of this, so that you get this cos and sine. Okay, so you have to transform the denominator of your S domain equation in terms of something like this. So because this is our target in time domain. Okay, so you take the expression of the denominator of the quadratic factors poles, this one. Okay, s plus 2s plus 2. So I mean this part of the function. Okay, you take that and try to express in terms of um, this. Okay, so this is the common or general term for the quadratic function. So you can express in terms of this. You can also express in terms of this. You learn this in mathematics already, and this must be equal to that. Okay, so if you solve for this, you will get alpha equal to 1 and beta equal to 1. Okay, so you can solve for this one. Beta squared plus alpha equal to 2, 2 alpha equal to 2. That means alpha equal to 1, and then you can use the rest to calculate beta, which is also equal to 1. So after you get that, so the partial fraction just now, so you get the value of b and c already. You get c equal to 2, b equal to 1. So you can express also the bottom part of the partial expansion to become like this in the form of something like this, so that you can use the Laplace table. Okay, but the problem now, okay, look at here, you have s plus 1 squared plus 1 squared. Okay, but on the top you have 2. Compared to this, for example, this one, so omega must be equal to omega, a must be equal to a, so something quite different. So what you need to do, if you need to separate this into two terms. Okay, so that is transformed to become like this. S plus 1, like this, s plus 1, you take another 1 from here, divide by this, of course you get this part. Okay, so combine these two, if you add together you should get this. Okay, and then something like this you can see here. Okay, for example, s plus 1 divided by this, so you get here, okay, will be equal to this one, s plus a, which is a in this case equal to 1, so a equal to 1, omega squared, omega squared equal to this one, so omega also equal to 1. So the first term you can translate into this, which is e to the power of a equal to 1 minus t, so cos omega also equal to 1, so you get this term e to the power minus t cos t for this part. Okay, and this part, it looks like a sign, a sign like this. Okay, in this case, a also equal to 1 and omega also equal to 1. So something like this, e to the power minus t sine t. So you get this term. Okay, and this one, of course, is an exponential term. This one, s plus a equal to 2. So you get this. Okay, so that's how you do for inverse Laplace if you have complex conjugate pair. Okay, so remember, if you have complex conjugate, then the solution must be in terms of sine and cos like this. Okay, so always try to express your function in terms of this, then you get the solution for that. Okay, for the residue method, I'm not going to discuss the theory of this, but rather I want to show you how to use MATLAB. Where is it? How to use MATLAB to calculate for that. So if you type help in MATLAB, help residue, wrong spelling. Okay, so help residue, so you have something like this. Okay, where if you have the transfer function like this, then it will express in terms of something like this with the partial fraction. So this is the residue. MATLAB use residue approach. Okay, so what you need to do, just copy this and put it here. For example, if you want to repeat just now for the case of non-repeated root, this one. Okay, so you must express that b represent the numerator of this. So the numerator multiplier, the first one is equal to 1, the second one is missing s, that means you put 0 for that, and then you have independent of s 1. Okay, so that's how you enter the numerator part. And denominator, this one is in terms of fraction of the roots like this, so you can use the command poly. Poly, that means to form the polynomial based on the location of the roots. The roots number 1 is -1, roots number 2 is -3, roots number 4 is number 3 is -4. Okay, and then when you return that, MATLAB will give you straight away the answer, what is the value for this. Okay, for example, for roots number 1, for this one, poles of -4, that means for this one, that means C, so associate to here equal to 5.667. Okay, so we can check here. So 17.3 is supposed to be 5.667. Okay, and then for the poles equal to -3, pole equal to -3, which is B in this case, will be equal to 5. So we check here, so it's 5. Okay, for the pole of -1, so poles of -1, what is it? This one, pole of -1, so the A must be equal to 1/3, so equal to 0.33 here. So that's how we did it using MATLAB. Okay, MATLAB use a residual method. Try this one. Okay, for the repeated factors like this, so at the top here we only have one term, but s squared, so that means for only s squared, s equal to 0, the free s multiplier also equal to 0, so we should enter 100 for the numerator. And denominator, you have something like this, you have double roots at -1, so -1, -1. Okay, and the third roots -2. Okay, when you return that, and it will give you straight away. Okay, so for the pole equal to -2, so the residual equal to 4. Pole of -2, that means this one, C, for C, -2, so C equal to 4. So it's agreed with that. Okay, and then for pole equal to -1, okay, this one is quite tricky because you have 2 -1 repeated poles, so which one first? Okay, always follow that the one with higher order multiplier will come first. Okay, so where is it? Okay, so for A, so for A is going to be -3, and for B will be equal to, where is it? Will be equal to 1 in this case. Okay, so this is the residue. So which one will come first? So it's according to the way you write here. So you write here the first one, second one. Okay, so the first one multiplier here, A, multiplier of A is supposed to be -3, and B is supposed to be 1. Okay, just follow the order the way we write here. Okay, for complex conjugate pair, like this, so you have to enter again. Okay, on the top, the multiplier will be equal to 2, 6, and 6. Okay, at the bottom here, we have two terms like this. One is complex, so we cannot use poly anymore. So instead we're going to use the function of convert, conv, to convert these two into one polynomial. Okay, so enter the multiplier for this 1, 2, and then close bracket, open again for the next one, so which is 1, 2, and 2. Okay, what's wrong? We have extra closing. Okay, so now MATLAB will give you something like this, which is in complex conjugate pair. Okay, for the first one, for the a is given here equal to 1, a equal to 1 for the root of minus 2. So just forget about this value of complex because it's 0 anyway. Okay, so we get for that one. But for b and c, is it expressed in terms of complex conjugate number like this. So what you have that, so you can go here into residual method, so you express something like this, so you can follow this mathematics, and you should also be able to express that in terms of cos and sine. So that's why I don't teach you this, because the mathematics is more complex compared to partial expression or partial expansion, partial fraction expansion. Okay, so but MATLAB will use this approach. Okay, so you can use MATLAB and also the partial fraction expansion. Okay, you can use both MATLAB and for residue and partial fraction. Okay, let's see how we're going to apply the inverse Laplace to solve for linear time invariant differential equation. So if you still remember, differential equation will represent a transfer function in time domain. So that means we can know the solution of the system response based on this inverse Laplace. So how we want to do that? So first, take this equation of differential equation, transform into Laplace domain. So after you get a Laplace domain, uh, you do the partial fraction, or if you need to multiply with the input, you multiply with the input first. After you get the final expression in Laplace, then try to use inverse Laplace using partial fraction expansion to take the inverse Laplace, and you know the time domain. Okay, let's see the example. Okay, let's say we have this differential equation. Okay, so the first step is we going to transform this into Laplace domain. So let's say this is the when we have one dot here, that means it's differentiate one level, two dot, that means differentiate twice. Okay, and this is the initial value given to us for this x. Okay, so first step, transform this into Laplace. So x double dot, so we differentiate twice, so put s squared, and this xs is the equivalent of that in s domain. Don't forget to minus the initial value, s at 0 minus x dot 0. Okay, and the value is given there. So x dot equal to b, x0 equal to a, so just multiply with s, plus the 3x dot. Okay, so again you differentiate only once, so you have 1s, and the x in S domain minus the initial value. In this case, you only have one initial value because just one dot. Okay, minus x0. Okay, plus here 2x equal to this side equal to 0. And then you do something like this. You group together the term. You substitute the value from here. Okay, and group like this equal to 0 again, and then you simplify the term, you add this with all these term, and then you end up with something simplified like this, and bring this side, this constant, okay, constant value here, constant multiplier here, bring to this side, you have that. Okay, and then you can express s by bringing this to that side. You have x s equal to this. Okay, so and then you simplify this using partial fraction expansion. Okay, just now in this case you a simple case because you have linear roots, so you just express this, factorize this to become like this, and then you can express in terms of this. Okay, by partial fraction. Okay, and then looking to the Laplace table, you know already this is going to be this exponential term. Okay, e of power minus t, and this is just a multiplier, so just bring over there using a linear theorem. Okay, so in this part, okay, delay now is equal to minus 2t because you have 2 there, so you have exponential term there and multiplier a plus b. So this is the expression for that in time domain. Okay, you have in Laplace domain, first you have transfer function. This transfer function, if you want to solve directly, we don't know how to solve this in terms of time domain, but if you transform this into Laplace to become Laplace domain to become like this, and then you rearrange to express in terms of this, and then use partial fraction expansion to convert like this, and then you can look at the Laplace table. Okay, you should get this equation as the solution to differential to the differential equation. Okay, so let's try another example. So let's say in this case we have this equation, so you have this transfer function. So you have the transfer function here, and you apply the input here to the transfer function. Before that, there's no input. Input equal to 0. Okay, it's only act on the initial value. But in this case, initial value is equal to 0. So there's no initial value in this case. So, but we have the input. Okay, remember this is 3. In time domain 3, that means you have step of 3. Because remember, if we check the Laplace table just now, so how to go for Laplace? Okay, Laplace table just now. So in time domain, if you have in Laplace domain, if you have, sorry, not Laplace. In time domain, if you have 1, that means in Laplace equal to 1 over s. 1, that means step function, unit step. So in this case, you have 3. That means step function of with the strength of 3. So in Laplace domain, it's going to be 3 divided by s. Okay. So we convert this into Laplace. The first one is s squared xs. The second one is 2s. You have 1 dot, 1s, 2s plus 5. Okay, all multiplied by x. So because all these are 0, so we don't have to take care of the initial value. It's all equal to 0. Okay, and in this side we have 3 over s. Okay, so you have 3 over s. And then x will be equal to this part, bring to that side. So you have xs equal to this equation. And then you solve this, but now you have complex conjugate here. Complex conjugate pair there. So that means we expect the sine cosine solution. Okay. For the first part, you follow the normal way to calculate. You're supposed to get this 3 divided by 5, 1 over s. The second part, okay, the quadratic part here. So if you solve using this the approach of partial fraction, you're supposed to get something like this: s plus 2 equal to this. Okay, as usual, you're going to separate this into two components because we expect to have sine and cos. Okay, so express this in terms of standard form like this. Okay, and of course at the top you have to put s plus 1 and you separate another one as we did before this for complex conjugate roots. Okay, so at the end you end up something like this and like this. Okay, here become 2 because we take this. Okay, it's supposed to be 3 over 10 but because we want 2 up here, so that we can express in terms of something, where is it? Okay, something like this. Okay, we want something like this. So we should have 2 squared there, so it's supposed to be 2 there, so we multiply by 2, so that's why you have 10 here instead of 5. Okay, so that we can express in terms of this. Okay, so you end up with a term like this, and then based on the table, okay, the first one, 1 over s, in terms of time domain is just a step which is 1, so just left 3 divided by 5. The second term, so is going to be sine like this, okay, with omega equal to 2 and a equal to 1. Okay, so e a power of minus t sine 2t. Okay, we have there e of power minus 1 sine 2t with a multiplier of this. Okay, similarly for this side, minus 3 divided by 5. Here, we compare to this, omega square equal to 2, that means omega equal to 2, then a equal to 1. So e of power minus t cos 2t. So this is the response of this system. Okay, you have the transfer function, apply this step, so you get this response in time domain. So that's the advantage of Laplace domain. So we transform from time domain into Laplace and then apply the input to that, so we can express the output in Laplace form, and then we take the inverse Laplace for us to know what is the actual response in time domain. So that's the application of inverse Laplace to solve differential equation. Later on in time domain analysis, you're going to use this to calculate the response of the system, which is more detailed later on with Dr. Hanafi. So that's all for this video. Thank you. Assalamualaikum warahmatullahi.